This will be another Legion session this week. So I wanted to continue the discussion that we were having last week, talking about how Legion performs its dependence analysis on physical instances that are not reduction instances, right? So if you recall the last time, what we were doing was we were looking at the materialized view class, right? Which is effectively, the data structure that we use to track all the users on a particular physical instance in a specific memory, right? And actually do the analysis to figure out, which operations are overlapping, or which, when you try to do a task or a copy that uses a physical instance, you want to find all the prior users that overlap with that on any fields or any index-based expressions, right? To actually be able to track, what dependencies you need to record on each of those things, right? And in particular, there are various different methods that we use to do that, right? So like last time, we were looking at this find copy preconditions, where if you're going to issue a copy that's going to use this particular physical instance, you need to find, an event that represents all the preconditions that, overlap with that particular copy that you're going to be issuing. And so today what I want to look at is actually start looking at add copy user, and then if we get time, we'll also probably look at register user as well, which is for tasks. And looking at how they actually, put users into the data structure that we actually use for doing this analysis, right? And just to refresh everyone's memory, right, like the main thing that we're going to be looking at today, right, the data structure that actually we use for tracking, the users of a physical instances is a bounding volume hierarchy, right, which is effectively represented by these expert view trees, right? Each node in this tree represents all the users at a particular index-based expression, right? And then, each of these nodes represents, tracks all the users below it some sub-expressions, right? They're using subsets of points and so forth, right? And, importantly, these bounding volume hierarchies only, have to be recorded along one path, right? So if you have like one expert view that's maybe dominated by several other expert views, it'll only be represented in one of them, right? So this like dotted arrow where this expert view is dominated by two of them up here that are potentially overlapping but not dominating with each other, right? This arrow won't actually exist in the data structure, right? You won't actually have an edge here that you'll have to traverse because you'll get it by traversing through this path, right? And so we've got this bounding volume hierarchy, which we looked at the last time, right? It stores all the users and each of these nodes. So today I want to talk about, actually answering a question that Manolis asked at the end of the last session, which was, are we guaranteed to have an actual, node in this bounding volume hierarchy represented for each of, the users that, or for the set of expressions for our index-based expressions, say for a copy or a task that we may be recording a user for, right? And so that's a very good question, and we're actually going to get to that today as we look at how we might actually record, a copy expression as a user in one of these nodes in the tree. Okay, so let's actually go take a look at some code here, right? So let's actually take a look at the add copy user call over here in add copy user. There we go. Right, so here's our materialized view call, right, with our add copy user. Right, we've got Boolean saying whether we're reading or writing. We might have a reduction op if we're not reading. Right, we have an event saying when this copy is actually going to be finished. We have a field mask saying all the fields that are being used. We have an expression which says this is the set of points that this copy is touching. Right, our operation ID that launched this copy, the index for the region requirement. A set of applied events that we'll be tracking and some tracing stuff and things like that. Right, and so, similar to what we saw last time with find copy preconditions, the first thing we check to do is check to see if we're on the owner node for this materialized view. If not, we're going to end up sending a message over to the node that actually is going to, that is the logical owner of this materialized view, right? So remember, each materialized view is, you might have many copies of it around the machine, right? But only one node, the owner node, the logical owner node, is actually the one that actually tracks the data structure, the expert view tree, right? So effectively, you're not on that node, you've got to actually send a message over there to actually do that, right? And that's what happens in this is logical owner branch over here. Again, we're going to skip the enable view replication. That's off by default, and so not relevant to what we're talking about during these sessions here today. So anything you see wrapped in the enable view replication is just off by default, and so we can skip all that. Right, so eventually, if once you do make it onto the owner node, what you get to this path down here, right? And effectively, what we're going to do is we create a little region usage, right, just to track, what are the privileges and coherence modes that we're using to actually issue this copy, right? And then we're going to add this copy user to the data structure, this add internal copy user. So let's actually go ahead and do that and take a look at what happens there. And you see there's actually an internal task user as well. We'll probably look at that hopefully later today, but let's actually look at add internal copy user here. Right, so we've got our region usage, are we reading, writing, reducing, with what privileges and coherence modes? We've got our index-based expression describing the set of points that are being copied. We've got our set of fields, right? This is the event that says when that copy is going to be done. The operation that launched the copy, our index for region requirement. Okay, so the first thing that we try to do here is we want to see, before we actually try to go add this user into this expert view tree that we've got, what we want to do is see, is there any node in this expert view tree over here that actually already stores exactly the set of points that we're trying to add here, right? Is this user expression already represented by some node in this bounding volume hierarchy over here? And to do this efficiently, what we do is we actually have a cache that actually helps you look up, for a given, index-based expression, is there already an expert view in this tree? So this expert cache data structure here is actually going to help us, do this quick lookup and see if there's already a node that represents, exactly the set of points that we want to do to record our user for. Because if there is, we can just go ahead and jump straight to that node, record our user there in that expert view node in the bounding volume hierarchy, and then we're done, right? But if there's not, then we're going to have to do something else, right? We're either going to have to add a new expert view node into this bounding volume hierarchy to be able to represent that, or we're going to have to potentially record our user in lots of different places all throughout this expert view tree to make sure it's actually stored, in all the nodes where some later thing traversing this bounding volume hierarchy needs to be able to see it, right? So effectively, this expert view cache, and let's actually take a look at this over here on this materialized view data structure here. Where is the cache? Here it is. Right, so we've got a little cache here that actually represents a mapping from index-based expression IDs to the expert view nodes in the bounding volume hierarchy. And it's protected by this expert lockup here, right? So effectively, when you go to access this cache, you actually will go through and try and, find all the nodes that, or look up in this, you can take this lock and then look up in this cache to see if you can jump straight to the node in the expert view bounding volume hierarchy to record your user, right? Because you don't actually have, if you're just trying to add a new user to this data structure here, right? You don't actually have to traverse this thing, right? You're just going to add yourself as a user on this node, right? So you don't have to go through all the nodes and jump down through the hierarchy to find it. You can just jump straight into the middle. Whereas last week when we were looking at find copy preconditions, to find all the preconditions there, you got to start at the root and traverse your way down and look for any interferences, right, to find preconditions. Okay, so effectively this cache is going to help us look up these nodes. Now we haven't actually looked at how this how this expert view tree, how this bounding volume hierarchy actually changes over time. Sometimes nodes when they become empty will get pruned out, right? And so you often and then new nodes can be added. So we have a max size on this cache, right, to effectively keep it, it keeps itself up to date, but then also it prunes itself out and removes nodes that are empty, occasionally. And so that there's a timer here that says every time you access this cache, right, effectively it'll try to figure out, have you done enough uses to try and prune out empty nodes in the tree and stuff like that. So you'll see some stuff like that. Bookkeeping code in here for this expert cache. In fact, let's see if we can see here, right? And so, yes, you can see if we find something in the cache that we've already, if we find a node in the cache we've already looked or that we're looking for, right, we're actually going to have to sometimes go through and prune things out at the end of this thing. But okay, so let's I'm jumping ahead of ourselves a little bit here. So we do this lookup in the cache. If we find our cache or find our node in the bounding volume hierarchy, we're going to be able to use it right away. So this target view here, it starts off null, right? But if we find it and we can jump straight to it, we're going to be able to use that to be able to do a quick lookup on the or quickly add ourselves to this to the bounding volume hierarchy. So I'm gonna say let's assume that we go through this path here first, and then we'll come back and look at the other paths where we don't find it, right? So if we find the target view, right, and it also has all the fields that we're looking, or it doesn't have any invalid fields that has or disjoint from the set of fields that we're actually looking for, right, we can record that we've got our target view. We'll talk about invalid fields hopefully a little later. But effectively, these are like, sometimes nodes in the bounding volume hierarchy can be invalidated for certain fields and new fields created and so forth. And so we need to check for that particular invariant there. Okay. So if we have this is the not has target view path, so we're going to skip this and jump down here to the has target view path. We'll come back to this, I promise, to talk about that path. Okay, but if we've actually got our node in the bounding volume hierarchy, we can make our physical user, right, which is effectively the thing that represents our particular use of this physical instance, right? We add a little reference and it's going to be added into the tree, which will keep that physical user object alive. And then we can jump straight to that node and record the current user. And let's just go take a look at that right now, just to refresh our memories. But if we look at expert view, add current user, right? It's a really simple thing. You grab the lock onside this node of the expert view tree, you get the set of current epoch users for this termination event, right? And you add yourself in there. And if you're the new user, right, you can add a reference, right? Because you're the first one, so you want to keep it alive, right? So that's really simple. And one thing that's worth pointing out is the reason this is so simple is that we presume that if you're doing an add copy precondition or add copy user, you've priorly done one of these find copy preconditions, which has already updated the current and previous epoch lists on the expert view nodes that we talked about last week, right? And what that means is that you can eagerly add yourself to the current epoch user list, right away, because something else has already done the filtering of the prior preconditions back to the prior epoch user list, right? And so effectively, that's an important optimization, and it's nice that we kind of do assume that if you're doing an add copy user, that is coming after a find copy precondition for exactly the same things on the same same expression, same fields, and so forth ahead of time. So we do try to maintain that invariant, and it is something that you do want to watch out for, from the calling side. But the copy fill aggregators that we talked about a few lessons ago, right? They effectively abide by this restriction. They'll always do one find copy preconditions, followed by an add copy user to each of the views, right? And so therefore, that allows us to maintain that particular invariant. Okay, so once you've added your current user, then you're done, right? And so that's a really simple path, and that's actually the common case, right? That's what happens in most cases. So let's jump back to add internal copy user. Okay, so that's sort of the fast path, right? We had our thing, we had a view, we were able to add our user right away, right? If we can remove the reference that we added right here to keep the thing alive, right? And if reference counts goes to 0, you delete the user and so forth. And then down here, this is the bookkeeping code that I mentioned. Effectively, if you have to update this cache and prune out stuff, right, you can do some of the work to start telling the runtime it needs to clean up that cache and so forth. Okay, so that's the case where we have a target view, where we hit right away in the cache. Now there's another way that we can have a target view, which is the cache might not hit, right? We might not hit in the cache. We might not have this mapping right away. But what we can do is, so let's say we come down this path and we don't hit in the cache, right? Let's check to see, if we can actually find an expert view in the tree that has a congruent expression to the set of points that we need inside of this bounding volume hierarchy, right? So just like the cache does a lookup based on the names of these index space expressions, right? So it says maybe this is a rectangle representing points 0 to 4, right? And there might actually be multiple index spaces that represent points 0 to 4, right? We can actually have multiple names for the same set of points, right? And so if that's the case, you might have a copy that comes along later that also is done on points 0 to 4, but don't align with the same name, the same index space expression, right? And if that's the case, you actually could potentially find a node in this bounding volume hierarchy that does represent exactly the set of points that you care about, but doesn't use the same name, right? And so that's what this path is doing here. There's actually a congruence test that you can do to actually go and find an equivalent node in the bounding volume hierarchy that exactly represents your set of points that you actually want to do this to add your user for, right? And so this find congruent view actually will go and do that test. We can actually go look at this this method here. Find congruent view, right? And so effectively what we're doing is we're traversing through the bounding volume hierarchy, looking for a node in this bounding volume hierarchy that exactly matches the set of points for our index-based expression, right? And so what you can do is you can effectively say, well, we can test ourselves first, right? And effectively check to see if the volumes are the same, right? We are guaranteed that this index-based expression is dominated by the set of points of this expr view, right? So we effectively, by doing that, we can because we have that dominance guarantee, we only have to check to see if the volumes are congruent to see if they're the same. And if they are, right, then we've actually found a congruence match, right? But if not, we traverse over our subviews, a little symbolic test to see if they're the same, right? Because it might have fallen out of the cache, but you might find the same name later as you're doing the traversal. If you don't, find yourself there, then you do an intersection, right? See if they overlap. Right, if there's no overlap, well then we're done, right? If the overlap volume is the same as the volume of our expression that we're traversing for, right? Then that then you can continue the traversal, right, and see if you're actually going to match, right? And effectively, or sorry, I should say if the overlap volume effectively is the same, right, as the expr volume that we're actually testing here, that means it completely covers the expr that we're trying to traverse for, right? So we can continue the traverse in that case. Right, and if it's less, we keep going down looking for a congruent view. Otherwise, if you actually matched exactly, right, then you've already found the expr view that you're looking for, right? And so that's a really simple test, right? And if you don't find anything that you overlap with, right, well then you didn't find any congruences, right, and you return null, right? So that's that's effectively what's happening there with that congruence test. You're effectively looking for a node that has the same set of points in your index-based expression that you would have found otherwise. So let's jump back to add internal copy user. Okay. Now, so maybe you find a congruent view, right? And if you find one, you do still have to check these invalid fields thing here, right? And if you don't find it, let's see. I'm just checking my remembrance of what's happening here. Right. Okay, yes. So there's still a check here to check to see if there's if the invalid views are up to date, and if not, we're going to go and update those. By doing this insert, you're effectively updating these invalid views to say there's new users on this particular mask. But if you found a congruent view, then we will get here to this this has target view, which will then send us back down to this path down here, right? And we'll go and record ourselves in that particular target view, that node in the bounding volume hierarchy, right? And later things will come through and find us. Okay, so those are two paths where we can actually find a particular target view. Now, there's a third path, which is you didn't hit in the cache, you didn't find a congruent view. And what do you do then, right? This has target view is actually going to end up being false here. And you see there is an else statement here, right? And what we're going to do here, this is one area where copies and tasks are going to be different. And I'll try and explain the philosophy for why copies and tasks are different, right? So if we jump back to our picture of our bounding volume hierarchy here, right? So copies can get arbitrarily complex, right? In the sense that you can get copies for all sorts of intersecting expressions between lots of logical regions that your tasks want to access, right? And it's expensive to make these view nodes in this bounding volume hierarchy. And so you don't necessarily want to make one for every intersection, of two logical regions, or I should say index spaces that your tasks actually want to access, right? And so for copies, we don't actually go and make new nodes in this bounding volume hierarchy if we don't already have an expression for them. And that was the question that Manolis asked at the last time: is are you guaranteed to find a node, when you go to add a user, in this bounding volume hierarchy, that there will be a node that exactly matches the set of points that you're trying to add your user for? And so the answer for copies is no. And we're going to go look at this, effectively add partial user path here in just a sec to show what happens in that particular case. Before I do that, I will say for tasks, though, we are going to add nodes because effectively, when a task is actually using an index space expression that exactly corresponds to an index space that the application made, right? And presumably that means something to the user and is important enough that they're going to probably launch several tasks that potentially use it over the course of the lifetime of the application, right? And so there, it's actually worth the cost of making a new node in this bounding volume hierarchy. For every new task that comes along that's using this physical instance, you actually want to go and make a new node in this bounding volume hierarchy if there's not already one there to represent it, because presumably you're going to come through and have some later task that's also going to use it again, and that sort of bears itself out. So when we actually look at add internal task user, right, which is the sort of the parallel version of this for tasks instead of copies, right, it will go through and make a new node if there's not already one there, and we'll go look at that in a minute. But for copies, we don't actually take that path. We effectively say, there's going to be too many, intersecting index space expressions to make nodes in this bounding volume hierarchy for all of them. And so what we'll do is we'll actually record our user on any expert view which could potentially interfere, with this particular index space expression. And so we'll actually record our copy user in several places throughout this bounding volume hierarchy to make sure that, it's accurately represented everywhere. So any later user that, any later copy or task that comes through and tries to use its instance will be able to find the prior expression that's actually being used. Does that make sense to everyone before I dive back in and start looking at what happens in add partial in this add partial user call here? Hopefully the philosophy makes some sense to folks. Okay, not hearing any questions or objections. So we're going to jump through this and actually take a look at this add partial user here. Okay, so let's actually take a look at this add partial user. This is actually going to traverse through the whole bounding volume hierarchy and record our physical user that we made, in several different nodes throughout that bounding volume hierarchy to actually be able to make sure that later copies and tasks that come through will find any interferences, that they need to in order to record a dependence on this prior copy that was done to this physical instance. Okay, so let's actually go look at add partial user. Okay, so effectively, there's actually some comments here that show what the philosophy is of add partial user, right? What it's trying to do is, you want to push this, you could record this user sort of like very, conservatively on all the nodes that it interferes with all throughout the tree. But that would be overkill to actually record it like on all the, like you could literally go through and say like, we'll record the user in the root. And then, for anything that it intersects with below, we'll record it in all those things as well. And then you traverse down and anything that it intersects with down at the next level, you record it there also. So you could record it like all throughout this tree, but that's actually excessive, right? What you really need to do is just like find the last, set of views where it actually overlaps, where the index space expression for this user overlaps with the bounding volume hierarchy to be able to record it, right? Because that's all the places where you're going to potentially have something that actually interferes with the user, right? So you can see what we say here is we're going to try and push this down as far down the expert view tree. You still need to find nodes that dominate your usage of this user expression, right? But effectively, you want to find the last ones. You don't want to do it throughout all the intermediate ones throughout the tree. So effectively, what you're doing is you're looking for all the ones, for the last node in this, the last nodes in this bounding volume hierarchy that dominate your expression, but not any of the intermediate ones, right? So say, for example, like, maybe our copy is dominated by this node, but not by this one. It only like intersects with this one, right? So you're not going to record, at the root, but you will record your user here, so that anything that comes through this traversal going down here will end up finding this user as on this particular node on this expert view. Okay, right. So effectively, what we do is we iterate over our subviews, and again we're checking to see do they dominate our user expression here that we're trying to traverse for, right? So we can, we try not to do subtractions as much because they're expensive, right? So we do lots of index-based expressions or intersections, right, with that. And then you can, test for dominance by looking at the volumes, right, to see if they overlap, right? So effectively, like, if your user expression, right, if the volume of this overlap between, the expression of the node that you're on here on this, this is our expression that we're traversing for. This is the expression of the node that we're on in the bounding volume hierarchy, right? And you test for you do an intersection, right? And you look for the volume of that intersection, right? If that's the same as the volume for this expression that we're traversing for, this user volume, right? That means it dominates, right? And we'll be able to continue this traversal, right? Interestingly, like, if it exactly dominates, right, the volume that you're looking for, then you can actually like add the user directly. Otherwise, you need to continue this partial traversal thing, right? And you might wonder, like, would this actually happen considering we've actually done the congruence test that we did before? And the answer is like, like, shouldn't we have found this when we did the congruence test before? And the answer is like, in theory, yes, but we actually released the lock between like doing that check for the congruence test and actually doing this traversal to add our user, right? So some other like task could have come along and added a new node to the bounding volume hierarchy in the meantime. So it is possible that you hit this, but I will say this case is probably pretty rare. That you did a congruence test, you didn't find anything, and then some other task came through and added a new node to the bounding volume hierarchy, and then you end up finding it, right? And during your later traversal, trying to add this partial user. So it's pretty rare, but it could in theory happen. So that's why you have to do this additional test here. Otherwise, effectively we found a node below us that still dominates the expression that we're looking for, right? And then we can continue the traversal, right? And if so, we filter out the nodes that we continue that traversal for, right? And if we've done all of our fields, then we're done, right? But if we get down here to the bottom, effectively these are the fields for which, this is the last dominating node in this traversal, and so we need to record our user at this particular place in the bounding volume hierarchy, right? So that's effectively the add partial user case. Right, it pushes users as far down, this bounding volume hierarchy as they can get, where you still find a dominating node for all the points in your expression, but you can get, effectively partial dominances, right? And that's why, I mentioned the last time, just to close the loop here for everyone, right? If I can type properly, I know where this method is, but I've forgotten what it's called. Let's see. Try to get the scrolling to work. Where'd it go? Right, has a local precondition, right? So I remember we looked at these two methods last time. We were looking for copy preconditions, right? Testing for preconditions of all the users in the epoch lists, right? And I mentioned that you still have to do these index-based expressions sometimes, right? And that's for the cases where effectively these user covers bools are false because we've had an add partial user, like in the case of the copy. So we actually have to do the intersection test on the sets of points, right? And this happens, in this case where you've got these partial copies that have been recorded in the bounding volume hierarchy, to effectively, be users that are partially dominated by a particular node in the bounding volume hierarchy, but aren't completely represented by all the points in that particular node. So anyway, that's the reason that this happens, this intersection tests happen, even though you might think that all the users, right, on each node are completely represented by their points. That's true of all the tasks, but it might not be true of all of the copies. So that should hopefully close the loop there from something that we talked about last time. Okay, let's see here. Let's actually take a look back at, so we did add copy, or we did add local, add internal copy user, right? Effectively looking at how we added, a new copy user for if you're doing a copy. But let's actually take a look at what happens with tasks now. Let's see. Let's jump to the right version of this method. Here we go. Materialize view, right? So effectively, we've looked at these two methods now. Find copy preconditions. So if you're issuing a copy, how do you find the preconditions for a copy? If you're, once you've issued that copy, how do you record a user on that view, right? On this materialized view to say there's a copy using this view. Let's take a look at the third method here for tasks, right? Which is register user, right? And right, this one is effectively a fused method, right? Which does the same thing that both of these two methods do, for tasks, right? Effectively, it finds all the preconditions for the task to run, right? And returns those as an application event, right? Effectively saying this is the precondition for running this task, right? And and then records the task as a user of this particular materialized view. So let's actually go go take a look at register user here. Okay, so, right, summary of our arguments here, right? We've got our region usage giving us our privileges, our coherence modes, and our reduction operator if we've got one. These are all the fields that we might be using for this task. Or for, we've got our set of points, our index-based node that we're actually trying to map. Right, and remember that an index-based node is a kind of index-based expression. So this is representing all the points we need. This is the unique ID of the operation that we're running. This is our the number of the operation in the parent context, right? Our context index. This is our region requirement index that we're mapping for. Most of the rest of the stuff has to do with tracing and other fancy stuff. The other important thing here is this termination event, right? This is effectively the event saying when the task is going to be done using this physical instance. So it's going to be sort of the post condition that we'll record as a user on this materialized view. So anything that comes after it will record a dependence on that particular physical instance. Okay. Let's see. We'll skip the collective path again, right? We'll do collective instances at some future stage. Again, just like everything else, right? If we're not on the logical owner, then let's see. I skipped something here, right? This is the case for handling. This is a very special case for handling. Effectively, if you've got an empty instance and it's and we're doing some symbolic tests, there's a very fast path out here, but this will hardly ever get run unless you're using output region requirements. So you can pretty much skip this. Let's see. This is the path where effectively, if we're not on the owner node, we need to actually send the message to the owner node to do this analysis, right? So if so, we package up all of our data, send that message on over to the owner node or to the logical owner node for this materialized view to do that analysis there. Right. Nice thing about this with Realm, we can make all our user events, right, and give ourselves the return results even before that message has been sent, right? So we can return right away without blocking. Okay. Again, skipping all the view replication stuff. At some point, that will all get stripped out, so we don't have to do that. More view replication stuff to skip out. Here, this part right here is the actual important part. Once we've actually arrived on the owner node, what do we do? Right, so the first thing we're going to do is we're going to find all our preconditions. This is going to look very similar to find copy preconditions like before, right? So first thing we do is we check to see, like, is there a use event? Like, is there any deferred allocation event? Effectively saying we can't start using this instance until the instance is actually ready. We get that from the physical manager, right? So we add that to our wait events if it exists. Right, and then the next thing we're going to do is we're going to find our user preconditions, right? And this method parallels find copy preconditions on the export view tree on the bounding volume hierarchy, the same as we did before. So find user preconditions will look, like effectively we looked at export view, find copy preconditions the last time. And if we look at find user preconditions, and I call them users, but really you could also call it tasks or find task preconditions. This method looks very similar to the method that we looked at last time for find copy preconditions. There's really mainly only one difference here, I think, which is that there's a termination event here to help us, avoid recording users or finding preconditions on the same task. That if we have multiple region requirements that look like they might be interfering with each other, right, then we can effectively filter those out. But that's pretty much the only difference between these two methods is that there's one extra mode of filtering here, for find user preconditions to avoid aliasing region requirements, and their copies and stuff like that. But other than that, there's really not any difference. This will do the same analysis that we looked at the last time, right? It'll look at the current epoch list, find all the things that that we interfere with, as well as checking for domination, right? If you find any fields that are not dominated, then you also have to traverse the previous epoch list. Right, and that happens, regardless of whether you're doing a partial expression or a full expression, and then we traverse down through the subviews and down to the bounding volume hierarchy and do exactly the same stuff that we did, for the find copy preconditions the last time. So this code, effectively, I'm sort of skimming over this because this is almost identical to what we looked at last week. All right, let's go back to register user here. Right, and we're skipping down to the bottom where we were before. Here we are. Right, so we traversed the tree, right, found any user preconditions to effectively, get our set of events that are preconditions for actually running running this particular task on this particular region requirement. Right, and once we've done that, finding all the preconditions, we can now record ourselves as a user of this physical instance, right? Because this task is actually going to be using this instance, right? And we know that, we're going to record this, event as a termination event to say, when this task is done using these particular sets and fields, set of points and fields and stuff, right? And so we have this add internal task user method here. And this one is the complement to add copy user that we looked at before. The difference here, like as I said before, is that this time, right, effectively, if we're going to go through and try and find the same, target view that we had the last time, right, and we do the same checks, right, we check to see if we can find it by name first in the cache, right, if so, we're great, right, but if we don't find it by name in the cache, then we're going to go through, we'll do the same congruence test, right, see if we already find an existing node that actually has the same sort of set of points that we're looking for in the bounding volume hierarchy for our expression, right? If we do, then that's great, right? We can reuse it. But if not, what we're going to do is, in this case, because there's a task and not a copy, we'll make a new expr view and then go and insert that into the bounding volume hierarchy to actually be able to update that bounding volume hierarchy with a new node, right, to represent this particular task, right? And then, because we're guaranteed we're going to make that, we'll look at this insert subview method here to actually show you how that actually gets inserted in just a sec. But once we've actually made that view, like either we found it or we made it. And notice it's atomic, by the way. It's all protected by this lock on the effectively the root of the tree, right? Effectively saying, we're going to do an atomic find, and then if not, add a new view and then record that subview. So we mutate the whole bounding volume hierarchy sort of exclusively here, right? Or I should say atomically, so that that way it changes in an atomic way. It's an atomic find or create. But once we've got our view, right, then this is easy, right? We can just record our user and we're done, right? Because we're guaranteed to find either find or create a target view that represents exactly the set of points that we're looking for our index-based expression. So this is where add internal task user is different than add internal copy user, right? Effectively, it's doing exactly it'll create a new view or create a new node in this bounding volume hierarchy for any index-based expression that our tasks are actually trying to use, because presumably we're going to have other tasks that come through and try to use them again later. That tends to bear itself out in most applications. Okay. So that part is all pretty straightforward, right? That's how we get our task users into the bounding volume hierarchy. Let's actually take a look at this insert subview method here to see how it actually does the insertion into this tree, right? So let's actually, right, effectively it starts at the root, right? The root, this current users, right? That's the root of the bounding volume hierarchy, right? And we're going to insert this new view for these new set of points, right? And we're actually going to call this this insert subview method. Okay, so we're effectively traversing our bounding volume hierarchy, trying to insert this new node into this bounding volume hierarchy. And unfortunately, we're protected by that lock at the root of the tree to make sure that this insert is atomic. So like, you don't have to do any kind of like fancy hand-over-hand locking. Presumably, inserts are fairly rare, right? So effectively, mutations of the bounding volume hierarchy or of the shape of the bounding volume hierarchy happen infrequently, right? And so we effectively just have like a big lock at the root of the tree to protect us when we do those, right? And then everything else is sort of just traversing the tree and not mutating the shape of it, right? And so we can, those happen with like the read-only lock at the root, right? And so that way we get, you don't have to worry about, mutations to the shape of this tree happening at the same time that traversals are happening to check for finding preconditions and stuff like that. Just something, I didn't feel like it was worth the complexity of actually trying to implement sort of hand-over-hand locking as we're trying to do this insertion. It was just a little too complicated and not worth it for the performance gain that you would get for it. Okay, so effectively, what we're trying to do here, right, is find all the subviews that which ones we dominate and which ones dominate us, right? If we find one that dominates us, we can traverse down through it. I say us. I say like imagine that we are this subview. We're trying to traverse down our bounding volume hierarchy and insert ourselves in here, right? And so like what we're doing is like, we traverse the root, presumably it dominates us, right? So then what we're going to do is going to test against all of our existing subviews of the root, right? And see if we dominate, or see if the new node that we're adding is dominated by any of these, right? If it is, we can just immediately traverse down one of these nodes that dominates us, right? And effectively add ourselves in that subtree, right? Alternatively, if we dominate, all of the subviews at this level, right, then we're going to insert ourselves as a new node here and make each of these things our subviews now, and then we'll become the only subview of the root, right? But then and I guess a third possibility is if we aren't dominated by any of these guys and we don't dominate any of the nodes at this level, right, then we're going to add ourselves as a new node over here on the side and record ourselves as a subview of the parent, right? So effectively, we're doing that test to see how to add ourselves, right? So we're going to check to see if there are any subviews, check to see if they overlap with any of our fields. If so, we're going to traverse, right? And this is where we actually have to pay attention to the fields, right, that are actually being used on these expert view nodes, right? Because each of these expert view nodes have some set of fields that they're also tracking, right? And so if we don't have overlapping fields, then we don't even need to consider ourselves with respect to those other nodes, right? So we can skip any non-overlapping fields, right? If so, now we do the geometry test, right? Do an intersection to see do we overlap with any of those these prior the subviews from this particular node. If there's no overlap, don't have to worry about anything, right? Now we check for domination by doing volume tests, right? See if we dominate or just intersect, right? So effectively, if the subview volume is equal to the overlap volume, then we dominate that particular subview, right? Right, subview is our new the new node that we're adding, right? So it effectively, if we found a node that dominates, the node that we're adding, right, then we're going to end up, adding that, it's going to end up going down below us, or we're going to continue the traversal in one of these dominating subviews, right? Otherwise, if we're dominating, right, then we're going to try and add that, that node below us, right? Effectively, the new node is going to subsume, this node below here, and we're going to remove it from this particular, entry in the subviews from the parent, because we're going to be the new dominator for that, right? And otherwise, it's just a normal intersection without either one dominating, right? And so, effectively, nothing interesting happens there. Right. And so if we had any dominators, right, then we're going to try and traverse down them and find one that dominates us. And there's a little heuristic here, right? You can see we're going to try and pick the one with the smallest bounding volume that dominates us, right? So effectively try to find the tightest subview, right, that effectively represents the set of or that most tightly bounds the new subview that we're trying to add here. That's just a heuristic. You can actually do some more advanced heuristics here to try and maintain some balance between subviews in this tree and try and keep your tree a little more balanced, right, globally, right? I don't actually try to do that today. That's an optimization for the future. So, effectively, if we do have multiple dominators to choose from, we will today just use this heuristic to pick the tightest subview. No matter which one you pick, you'll be correct, but this is just a performance optimization there. So we try to find the one that's the tightest. Right, and if we actually get to this place here, right, then effectively we're just going to be, this is the case where we didn't find anything that dominates us and we didn't dominate anything else, then we're going to add ourselves as a new subview on this particular node in the tree. Effectively, we become we didn't dominate any of these guys and none of them dominated us, so we'll become a new subnode of the node that we're traversing right here, right? And in some cases, we might have to prune out some of the nodes that we dominated, and we update some of the data structures and so forth, right? So anyway, that's how insert subview works to update effectively the shape of this expert view tree, to actually add new nodes for tasks that come through and introduce new index-based expressions they actually need to traverse. Okay, so let's see. I think that it's probably a good stopping point for today, because we've effectively covered how we add users for both tasks and copies, and how we find preconditions for both tasks and copies on these bounding volume hierarchies for representing physical instances. And I don't want to start a new topic for the rest of today. So, what questions do you guys have about what we talked about? Is there something I didn't cover that should be made more clear? How How about I pick on Manolis first? Manolis, did you get your question answered from the last time?
I think so. I got a little lost, I'll be honest.
Okay.
So I'll need to go back and review, but I think I'm covered probably.
Okay. You get the idea of like you make new nodes for tasks and not for copies.
Yep.
Okay. Yeah, I do think this code probably. I do think like trying to move this bounding volume hierarchy more to being a axis aligned bounding volume hierarchy is probably the next cleanup step to do for this. I do think it'll clean up some of this index-based expression tests that we do today to make them much simpler. And I do think like the fact that most physical instances are represented by rectilinear pieces already, right, will actually help that process. We talked about that a little bit last week, but I think this code definitely can be refactored to clean some of that up and make it probably a little easier to understand without having to do all this like abstract index-based expression tests and actually do things rectilinearly on ND rectangles. So. Okay. Any more questions? Going once, going twice? If not, try to have a realm session next week. We'll see how that goes. See if I can organize that. If not, we'll do another Legion session. All right. No other questions? Talk to you guys next week.